What's up, everybody? Welcome back. Moving on to the next section, we're now going to be talking about polynomial inequalities, and I'm going to jump right into an example. So we got 2x cubed minus 5x squared plus 2x plus 5 is greater than negative 2x squared plus 5x plus 3. So if you notice, polynomial inequalities very similar to polynomial equations, but instead of an equal sign in the middle, you'll have a greater than sign, or you can also have a less than sign, or a greater than or equal to, or less than or equal to, right? But in this specific example, we just have a greater than sign. So like polynomial equations, what you want to do is you want to take everything and bring it over to one side. So you're just left with a 0 on the other side. So I'm going to take these three terms on the right side, bring them over to the left side. So let's rewrite this left side here. So we got 2x cubed minus 5x squared plus 2x plus 5. I'm going to bring this negative 2x squared over. That becomes positive 2x squared. Positive 5x, bring it over, becomes negative 5x. Positive 3, bring it over, it becomes negative 3. Then we still have greater than. And now we have 0 left on the right side because we brought everything over. And now what you want to do is you want to simplify this. So you want to collect the like terms, simplify them. So notice 2x cubed, there's no other x cubed here. So 2x cubed is already simplified. Negative 5x squared plus 2x squared, right? Those are like terms. Those would simplify to negative 3x squared. 2x, negative 5x, positive 2x minus 5x, that would give us negative 3x. And then we have positive 5 and minus 3, which would give us 2. And then we still have greater than 0 on the right side. And once you're at this step, once you have a polynomial on one side of the inequality and then 0 on the other side, what you want to do is you want to factor this polynomial. So let's label this polynomial 2x cubed minus 3x squared minus 3x plus 2. Let's sort of forget about the inequality now, and we'll come back to it later. Let's just focus on factoring this. So first thing you do when you're factoring is you want to see if you can take anything out. Can you take out any constants? Well, no. Can you take out any variables? No, because of this constant at the end. It doesn't have an x attached to it. Right, so that's the first step. Now notice how this is a cubic. So you want to check whether you can potentially factor this by grouping, but if you try by grouping, it's not going to work, unfortunately. So what you have to do is you have to use the factor theorem. So you got to start plugging in a bunch of numbers. So you got to try like f of 1, f of negative 1, etc., etc. And then if one of them equals 0, then we know it's a factor. So if we plug in f of 1 for all the x values, we get negative 2. So we know a k value of 1 would not be a factor. If we plug in negative 1, though, for the x values, we get 0. And by the factor theorem, since f of negative 1 is equal to 0, we know that x plus 1 is a factor of this polynomial here. So our next step is we find out how many times does x plus 1 go into this polynomial here. 2x cubed minus 3x squared minus 3x plus 2. And when you do the long division here on the side, the quotient you end up getting is 2x squared minus 5x plus 2. I didn't go through the actual steps, but I wrote them down for you. We've done plenty of long division in the chapter before, so you should be pretty comfortable at this point doing this. Now, since x plus 1 we know is a factor, it makes sense for us to get a remainder of 0. You should be getting a remainder of 0 whenever you're factoring. If you're not, then something went wrong in your algebra. Or x plus 1 might not be a factor. So, what does this mean? So if we erase this, basically, we've taken 2x cubed minus 3x squared minus 3x plus 2, and now we have split it up into x plus 1 and this quotient here, 2x squared minus 5x plus 2. And then when you factor this quadratic here, it actually factors smoothly into x minus 2 and 2x minus 1. So we've taken this polynomial and we factored it into these three terms. So now let's go back to our inequality up here. So basically what we've done, we took this polynomial and then we factored it into x plus 1, x minus 2, 2x minus 1. And this, we're still finding when is it greater than 0. And when you get to this point here, where it's factored, it's a factored polynomial on one side, 0 on the other, and it's an inequality. There's actually two ways of doing this. You can do it by graphing, or you can do it by something called a sign chart, and we're going to go over both ways. So I'm going to show by graphing first because we already did graphing in the previous unit. So it will be a nice continuation of that. So if we were to take this polynomial here and then graph it, how would it look like? Well, notice how this polynomial has an odd degree, a degree of 3, and it has a positive leading coefficient. So we know the end behaviors, it's going to be from quadrant 3 to quadrant 1. And then from this standard form here, we can tell that the y-intercept is going to be 2. If we plug in 0 for all the x's, we'll just be left with 2. If we plug in 0 for all the x's here, multiply the brackets, we'll get 2 as well. So the y-intercept is going to be 2, so let's label that there. And then what are the x-intercepts going to be? Well, we can tell from the factored form. The x-intercept here is going to be -1, this is going to be +2, and this is going to be +1/2. So if we label those, so we got -1 here, we got 1/2 over here, and then we got 2 right there. Right, so if we draw this out, it's going to look something like this. Right, so we took this polynomial and we graphed it. And now what they're asking us is, when is this polynomial greater than 0? And what this means is, when is this polynomial above the x-axis? When are the y values going to be greater than 0? So you may want to write that out. That's another way to look at polynomial inequalities. They're asking for when is it greater than 0, when is it above the x-axis. If they're asking when is it less than 0, they'll be asking when is it below the x-axis, when are the y values negative. Right, so when is this polynomial above the x-axis? Well, it's above the x-axis here, right, in this interval, and also right here. So the answer to this question, when is the polynomial above the x-axis? Well, the y values are positive between an x value of -1 and 1/2. Or when x is greater than 2. All of the y values are positive. So these are the answers. This is the answer to this question, to this polynomial inequality. Now, an additional remark I want to make to this answer, what if this polynomial inequality was greater than or equal to 0? How would that change our answer? Well, then, what this is asking us is, when is this polynomial function going to be greater than 0, above the y-axis, and equal to 0? So at these points here. Well, it's equal to 0 at -1, 1/2, and 2. So we would have to include those values in our answer, right? Because at that point, -1, at that point, 1/2, at that x value of 2, this polynomial equation is equal to 0 as well, and they are asking that. But because they only asked us when is it greater than 0, we don't include those x-intercepts. Now let's move on to the second way to solve this polynomial inequality, and this is going to be sort of new, so we can do it with something called a sign chart. So we'll do it this way, and then we'll compare the answer that we get with the sign chart with the answer that we got the first way we did by graphing, And hopefully the answers will be the same. Now, the way a sign chart works is what you want to do is you want to take the x-intercepts of a polynomial and then put them as columns. So the first thing you got to make sure is that your polynomial inequality is in this form. You got 0 on one side, and then you have a factored polynomial on the other, so you can actually get the x-intercepts. And here's how it works. So what you do is on the furthest left side, you start out by writing negative infinity, and then you write out all of the x-intercepts in order from lowest to highest. So notice these are sort of scattered. So the lowest one is -1, then comes 1/2, then comes 2, and then after you've written out all of your x-intercepts in order, at the end, on the right side, you put positive infinity, right? So negative infinity, all of the x-intercepts, positive infinity, right? And sometimes you'll have more than 3 x-intercepts. We'll do polynomial inequalities in the future. We'll have like maybe a degree of 4 or 5, but in this case, we only have 3. So what you do for these is now you just write, or draw rather, columns for each of them. And then once you have the columns done, you want to draw the rows, and the rows are going to depend on the factors here. So all you're going to do in each row is write the actual factors. So the first factor is x plus 1, right? The next row here, we'll write the factor x minus 2. And then over here, we would write the factor 2x minus 1. Now the order of these doesn't really matter. It's not as important as the order when we are writing the x-intercepts for the columns. And then the last row is just going to be the actual polynomial. So basically all of these multiplied out. So x plus 1 times x minus 2 times 2x minus 1. Now, another remark I want to make about this table is if you have something in front here, like a -4, you want to have that -4 as its own row. So we would write -4, x plus 1, x minus 2, 2x minus 1. So we would have another additional row, and we would include this -4. But in this case, there's no constant in front. So these are the only factors we write out in the rows. Now what you want to do is you want to figure out what's the sign, right? A sign chart. This is where the name comes from. What's the sign of each of these factors in between these intervals? So let's start off with this interval here, from -infinity to -1. What you want to do is you want to pick a number between -infinity and -1. So let's say, I don't know, -2. If we plug in -2 for x plus 1, -2 plus 1, that is -1, so that is a negative number. So we would just put a negative sign here. Now let's pick a number between -1 and positive 1/2. An easy one to work with is 0. If I plug in 0 here, 0 plus 1 is positive 1, so that would just give us a positive number. A number between 1/2 and 2, 1. If I plug in 1 here, 1 plus 1, that gives us 2. That's a positive. And then between 2 and infinity, so let's say a number like 3. If I plug in 3 here, 3 plus 1 is 4. That's another positive number, right? And then we can use these same numbers, -2, 0, 1, and 3, and then plug them into the rest of the factors. So -2 minus 2, -4, that's a negative. 0 minus 2 is -2, that's a negative. 1 minus 2, -1, that's a negative. 3 minus 2, positive 1, that is a positive. Then moving on to this factor, -2, if we plug it in for x, 2 times -2 is -4, minus 1 is -5, that's negative. 0, if we plug it in here, we get -1, that's negative. 1, if we plug it in here, we get 1, that's positive. And then 3, if we plug it in here, we get 5, which is positive. So once you have the signs for each of the factors of the polynomial in their respective intervals, to figure out the sign of the actual polynomial function, the whole function, you just take all the signs and multiply them. So a negative multiplied by negative would give us a positive, and then that positive number multiplied by negative would give us a negative number, right? Positive times negative. These two negatives turn into a positive times a positive. That gives us positive. Positive times positive. That gives us a negative. Then positive times positive. That gives us a positive. So now the most important part of a sign chart is this last row here. That's the one that we are concerned with. That's the one that's going to give us the answer to our question. So when is this polynomial function greater than 0? Let's go back to our original inequality. Well, it's going to be greater than 0 when this polynomial is positive. And when is it going to be positive? Well, it's going to be positive in this interval and also in this interval, right? So in between -1 and 1/2, the polynomial is positive, and between 2 and infinity. And notice how that is the same answer that we got the first way by graphing, between -1 and 1/2, and when x is greater than 2, right? From 2 to infinity. So those are your answers. And if they were asking us when is the polynomial less than 0, from -infinity to -1, and then from 1/2 to 2, those would be our answers if the inequality was switched. Right? So the answers to this, here we put it in interval notation. Let's put this in set notation. So basically, this polynomial is positive when x is between -1 and 1/2, and we would put that, actually, you know what? Let's write it over here. So when x is an element between -1 and 1/2, notice how we are putting circle brackets, right? Because it's not inclusive of the -1 and 1/2, because this is just greater than 0, not greater than or equal to 0. Or when x is an element from 2 to infinity, this interval right here, right? So two different ways to write this solution. You could write it in set notation, or you can write it in interval notation. Both of these answers are the same, and we did it in two different ways. We did it by graphing, and we did it this new way by a sign chart.